Hello everyone, welcome to the GATE NPTEL lecture course. Today we are going to learn the concept of interference of light and we will solve some questions based on this concept. So before going into this young double slit experiment, which is the main focus of today's presentation, so we will start with an interference. So you are basically familiar with this interference from your 12th class. It's the superpositions of waves. So whenever you have two or more waves, and you you have seen these two or more waves can be represented by this E vector and E2 vector in previous EMBF classes. So whenever you have two or more waves, then they will superimpose on each other, and the resultant amplitude will be larger or it may be smaller than the individual wave, depending on what is the phase difference between these two waves. So, superpositions of wave will give another wave which is have different amplitude and it may have different frequency as well. We are not going to talk about the frequency part here. So we kept our frequency part constant. So only focus of interference is just to change the phase of the wave. So
मैम
here,
मैम
yes,
थोड़ा फेज टर्म समझाना.
yeah.
फेज टर्म. व्हाट इज द फेज?
Okay, what is the phase?
यस मैम.
So if you see any wave, then it so basically we can represent any simple wave like E naught cos delta. The argument of this cosine function, this is generally known as phase. But if you try to visualize it, you just try to see what is the value of this function at this here. So the value of this function represents the amplitude of this wave, and what is this function vary with time. So what is uh, its value at time t1 and t2? This will depend on phase. For example, let's say you have a wave which is E naught cos delta, and at some time t0, your phase is 0. So your amplitude is E0. You can say that your amplitude is E0. But another time t1, your phase will get changed and it will become pi by 2. So if at that time you're in, if this is the time t, then this is the phase variation. It will become 0. So your wave will vary like this. So it have its amplitude get varies. So the variation of this amplitude with time, this is known as phase.
ओके मैम, क्लियर.
So for example, here these two waves have same phase at time t equals to 0. So these two waves have the constant phase relationship. At time t1, these two waves have the same phase relationship. So therefore, they will superimpose each other to give another wave which have larger amplitude. This will known as constructive interference. But if your phase is such that at time t equals to 0, the amplitude is 0, and at the time t1 the amplitude of first wave is high, but at time t1 for this wave amplitude is low. So when that means if these two waves have a phase relationship which is opposite to each other, so kind of 180-degree phase. So whenever you have 180-degree phase, it's like amplitude flip along this amplitude axis. There is a wave which is flip along this axis. So the resultant wave will be subtraction of that, which is known as destructive interference. So, as we study in electromagnetic waves, we can represent any waves in something like this. Cos k z minus omega t plus phi. This will control part of this wave, which is how much close your oscillation is. And kz will control the variation with respect to z, and phi is the initial phase. That means at time t equals to 0, what is the phase of this wave? At time t equals to 0, what is the phase of this wave? So these terms are constant. For example, you may have waves which have some amplitude time at time t equals to 0, but another wave which has amplitude this one. So these phi 1, phi 2 are the initial phase of the wave at time t equals to 0. This as the light propagate, then this phase will get changes according to this relation. Interference is the superposition. So we just take the E1 vector plus E2 vector, which represent the superposition. So we'll take this vector and plus this vector, this will become square. And to simplify this expression, what we do is we take the t dependence part separately and separately. So and we apply this identity. Cos x2 can be written as cos x1 cos x2 minus sin x1 sin x2. So when we apply this, first term will become this term will become this and this term will become this. We take cos omega t terms sin omega t terms together. So this is our expressions for the superpositions of wave. So let's assume that this is some constant cos E0 cos alpha. So we can take it as a constant because time dependence represent how the function is vary as a function of time. This will represent the amplitude. So we can represent E0 cos alpha as this term and this term as E0 sin alpha, where alpha is some phase. Just we can calculate the alpha later. So if we take this term and this term and we square it, add it, so we will get E0 sin square alpha cos square alpha will become 1. Similarly, this term is square and this term is square. So when we take this term square, E0 1 square cos square term plus E0 1 square sin square term. This term will become 1, so we are left with E0 1 square. Similarly, E0 2 square. And then there are cross terms also. E0 1, E0 2, cos kz1 plus phi 1, sin kz2, phi 2. Similarly, this term. And then we apply this identity, cos phi 1 x1 plus x2, this term. So we combine this term. So this is the term that is coming after superposition of these two waves. So the amplitude E0, which is the resultant amplitude of these two waves, is the combination of amplitude square of first wave, amplitude square of second wave, plus this cross term. This cross term is responsible for the interference phenomena that we see. And if we put this term as E0 cos alpha and the second term as E0 sin alpha into this term E, so we are left with E0 cos alpha into cos omega t plus E0 sin alpha into sin omega t. So E will become again E0 alpha plus omega t. That means our resultant is also a wave, but its amplitude is given by E0 and its phase is given by alpha. So here, if you look at this term E0, which is given by this, so we can also know that the intensity I is directly proportional to the amplitude square. So we wanted to see how the intensity will vary. So E0 square is E0 1 square. So if I1 represent the intensity due to one wave, I2 represent the intensity due to another wave, I just take K to remove this proportionality factor. I hope you know if we wanted to remove proportionality factor, we can introduce any constant. So I1 is the intensity due to first wave, I2 is the intensity due to second wave, and we put this into this expression back. So we are left with this I1 plus I2. So this is the intensity variation due to the superposition of these two waves. And cos delta is the term which contains the phase difference, which is the initial at time t equals to 0, and the phase difference that is accumulated at the wave propagating z direction. So this is also written as 2 pi by lambda into part difference. Part difference is Z2 minus Z1 is the one which is the wave accumulated as a function of time t. So by taking, actually, delta will also contain another term, this one. So this is the intensity that we are going to see. So whenever delta is a function of 0, 2 pi, 4 pi, so this term will become maximum I1 plus I2, 2 times of square root of I1, and which will make a whole square here. Similarly, when delta is plus minus pi or plus minus 3 pi, it will become minimum intensity. So you are familiar with these things, maybe in your 12th. I just try to again do these things. So the phase difference delta is 2 pi by lambda into path difference plus some constant term, which is always going to be constant. So the necessary conditions for the interference is coherence. And what we mean by coherence is phase difference does not depend on time t. For example, if this wave has a phase phi 1 at time t1 and this wave has phase phi 2, or you can say theta 1, let's say, and this is theta 2, then another time t2, this again have to have theta 1 and this has to have theta 2. It will not change to another value. So your phase difference, which is initially theta 2 minus theta 1, it is again going to be stay with theta 2 minus theta 1 as the time is changing. So this will known as the coherence. The phase relationship between these two waves will remain constant as a function of time. So what if your phase is not constant? For example, at time t equals to 0 and we have some phase relationship between them, which is let's say delta theta. At time t equals to 0, this is delta theta. But at time t1, relationship gets changed and it will become delta theta 1. So with delta theta, what you get is that the crust is you will get a super constructive interference. So if you have two waves and you try to capture it by placing a camera in front of them, so at time t equals to 0, there is a maximum intensity, but at time t equals to delta theta 1, the relationship will get changed and you will see minimum intensity. So I think you know that a camera always have exposure time. So if the exposure time of your camera, basically what it represent is at the camera then is try to capture picture, it will capture frame by frame. And in exposure time, it will tell you how much frame it will going to capture. So if your time t0 and t1, let's say it's 3 seconds, and within 3 seconds, your phase changes such that your intensity will change from maximum to minimum. But your exposure time of camera is fixed. It is 5 seconds. So your camera will see? It will see the minimum intensity, which is the later one. It will not see that there is a maximum intensity because the time lapse is 3 seconds. So basically, you see average of these intensities. And so therefore, you will not see any kind of interference pattern. It will come sometime maximum, it will come minimum, and your camera will integrate everything. So the phase difference should, no, should not change with the function of time. And this is lead to coherence in wave, and only then you can see interference pattern. Second thing is the monochromaticity. So basically, it's represent how, for example, what is the bandwidth of your source. You are familiar with this laser. Lasers have different wavelengths. For example, red color laser has a wavelength of 633 nanometer. Similarly, green color has a different wavelength. Yellow has 533, I guess. So it depends on the wavelength, monochromaticity. And this is a function of temporal coherence of light. So for example, if this is your wave, this is the case for laser. Laser have a very smaller bandwidth, and that means it will remain a phase relationship for a very long time. But if you have another source, it will have some glitch at time tc. So within this area, these two waves have phase relationship, but here you will see a glitch, and due to this, the phase relationship get broken. So within this time up to which the phase relationship maintain, this is what is known as the coherence time, and this is known as temporal coherence as well. So it depends on the bandwidth of the source. If the source bandwidth is very narrow, as in case of laser, then you will have very high temporal coherence. If it is have very wide bandwidth, then the temporal coherence will reduce it. So basically within this region you can see interference pattern, and here the interference pattern will again get switched So you will not see and then again see interference pattern when the relationship is kind of maintained. So the temporal coherence is a function of bandwidth. Here bandwidth is represented in terms of frequency. So basically you can also represent in terms of wavelength. If you have white light source, for example, it has 7 colors. That means it is started from lambda 1 and it will go to lambda 2. So bandwidth will be lambda 2 minus lambda 1. This is in terms of wavelength, but the standard way is to represent in terms of frequency. And we already know that frequency is given by c upon wavelength. So temporal coherence is a function which is represented by 1 by delta nu. Delta nu is what is this? Given by delta nu is c upon lambda square into delta lambda. Delta lambda is this bandwidth. So when if you are familiar with that, you can see interference pattern with laser, but you can also see interference pattern with white light, provided your wavelength, your path difference should be less than the coherence time. We will see in case of double slit how this thing will matter. It's a really important concept when we try to see whenever the interference pattern is going to form or not. And another one is the polarization. Your polarization has to be same. For example, if first wave is polarized in x cap direction or x direction, then the second wave has to be polarized in x cap. If the second wave is orthogonal, for example, in y cap, then there will be no interference pattern. So polarization has to be same. So now come to the young double slit experiment. So before going into young double slit experiment, so what will happen if you have a just one slit or single slit? For example, you take a cardboard and you place a hole inside it, and then you shoot a laser inside this hole, and you place a screen or another cardboard to see what will happen. So what you see on this cardboard is just the intensity of light within the resin of this hole. So you will see the image of this slit if you take a laser and you will switch on inside this. But if you started to try decrease the size of this slit such that it will become of the order of wavelength. Here the size is too large. For example, if your wavelength is 0.5 micron and the slit width is, let's say, 1 centimeter. So you will see only the slit image on the back side. But if you take and that you start reducing the size of this slit such that it will be of the order of zero point 0.5 micron, then you start seeing diffraction pattern here. You see intensity not only in this resin where you have the hole, but also the resin which is beyond that. And the intensity kind of start decreasing as we move away from this central resin. And this kind of pattern where intensity is very in this way, it's known as the diffraction pattern of light. So whenever you have a single slit, you are going to see diffraction of light. So what happens if you have a double slit? So basically this is a single slit interference. You have plane wave which is passing through a very narrow slit and you see the intensity variation and this is known as the diffraction pattern. So what happens if you have two slit? One slit will give diffraction pattern. So basically, and the another slit will give another diffraction pattern. And whenever there is this phase relationship match, then there will be an interference, constructive interferences form. And whenever the phase relationship is opposite, then there is a destructive interference pattern. So the interference pattern have the fringes which are of equal intensity. The intensity variation have equal amplitude in case of interference whenever you have these two slits. But in case of single slit, the intensity variation is such that you have maxima at the center and the intensity will dies down as a function of distance from away from the center. So this is the difference of the pattern that you see in double slit experiment. Now these fringes width are of equal width and you have equal width. So this is the derivation you are all familiar with, but just do it again. So you have two slit S1 and S2. They are placed at a distance D and you place another screen at a distance capital D from these slits. And you have some source like bulb. It may be light bulb also if you take a very small narrow slit here to pass this light bulb light intensity. So basically the light which is coming at S1 and S2, they are in phase. So you are going to see interference pattern at the position P or anywhere onto this screen which is placed here. So this is the kind of interference pattern. So we have to find what is the position Y of this fringe it from the center, what is the distance of this fringe from this center. So if how do you know there is a bright fringe or a dark fringe is going to form at the position P? The condition is that the phase difference, if we have a one wave which is coming from S1, we have another wave which is coming from S2. The phase difference between the wave which is coming from S1 and S2 has to be, you know, it will be equals to n lambda if we wanted to see bright fringe, or it will be equals to n plus 1 lambda by 2 if we wanted to see dark fringe. And this condition is coming from this formula itself. I think Arvind told you this formula. If you put delta equals to m pi, yeah, this is given here. So delta equals to m pi means, for example, delta equals to 2 pi. Delta is the phase difference. So 2 pi by lambda into path difference equals to 2 pi. So that will give you path difference equal of the multiple of lambda. Similarly, if for the path difference, whenever it is a multiple of lambda, it will give you constructive interference and you will see bright fringe. And whenever it is an odd multiple of lambda by 2, you will see dark fringe. So we have to know what is the path difference between these two waves. And once we know path difference, we will put it as equals to n lambda to see the condition for the bright fringe. And the path difference is the light travel path S1P from this source and it will travel a distance S2P from this source. So it will be S2P minus S1P. And we will take a blue triangle, then S2P will become t square plus y square, y plus t by 2. Similarly, S1P will become t square plus yn minus t by 2. So this is the derivation. We will calculate S2P square minus S1P square 2y1d and then a square minus b square formula is used a minus b plus b. And whenever capital D is much greater than small d, that means your screen is placed greater distance compared to these sources. In that we can take this distance to be equal. And when we put this S2P as 2D in this equation, the part differences comes out to be y and d by d. So n represent the nth fringes. So whenever we put this part difference y and d by d is equals to n lambda, the position for nth bright fringe will become equals to lambda d by d. And similarly for minimum fringes. And fringe width will represent, we just take, this is the fringe width. So we will, or you can say what is the fringe distance between two bright fringe, center fringe. So you will calculate what is the position of first fringe and then you calculate what is the position of second fringe. Next one and you just subtract them to calculate the fringe width and this comes out to be lambda d by t. So this is the case you are done in your previous classes, maybe in 12th or BSc, but the case that is new is this one. You are given two waves and they are at, uh, you know, meet at an angle theta 1 and then you have this second wave which is made at an angle theta 2. And since these are two waves, they will superimpose, they will interfere. So you have to tell what is the fringe width in this case. So this one is different from what we have done earlier. So how do we calculate? So we will go back to the initial state, how we started. So let's take the simple case when these two angles are theta and K1 magnitude is same. Magnitude of K1 and K2 is same, just the direction is different. So if you look at the direction of this case, K1 has the direction Z cap. You can say that K1 cos theta into this one, K1 sin theta. So you can also write K vector as, since its direction is negative, so minus x cap K sin theta plus z cap K cos theta. Similarly, you can also say for K2. K2 is moving in this direction, so it has two components. One is z in, another one in x cap. So x cap you have K sin theta. Since this angle is theta, this is theta. And in z cap K cos theta. We write E1 vector, which is K dot R minus omega t. For the first vector, this is K vector. So we multiply with R. This will give Kx, Kz, and omega t. Similarly, for E2, we will write our vector K2 dot R. So we also assume that the amplitude is also same for these two waves. E01 equals to E0. So what we do is we again separate the time dependence part and this x dependence part, and then we open this formula using trigonometric calculation cos x1 cos x2 plus sin x1 sin x2. So this will cancel this sine component part for both the cases. So the resultant E will become 2 is 0 cos kx and cos kz minus omega cos kz cos theta minus omega t. Now if you look at your resultant E has to be a function of cosine of omega t. That means this term and this term will represent a wave which is moving like this, and this term which does not have any time dependence, this will represent the amplitude of this wave. So this is the amplitude. Now this time amplitude is also a function of cosine. So the intensity I, which is directly proportional to amplitude, will become cos square kx sin theta. Now this is the phase terms. The part difference is given, phase is equal to 2 pi by lambda into part difference. So k represents 2 pi by lambda. That means x sin theta is the part difference. So whenever x sin theta is m lambda, that will represent the condition for right fringe. So and for the mx fringe, this is the condition. For the next m plus 1 fringe, this is the condition. And the fringe beta, which is xm minus xm plus 1 minus xm, and we just subtract these two terms, and this is the fringe width. Now fringe width will become function of lambda by sin theta. So this time your fringes are not a straight line, they are at an angle, something like this. So this is the case. This is interesting. Till now it hasn't come in the gate exam, but no one can stop it to came. So next come to this another concept. This concept is used in the gate exam, which is there is one question based on this concept in gate 2022. So just what it says is whenever you have temporal coherence, you can assume that you are going to see fringes. For example, if you have this double slit here, S1 source and S2
Hello,
source,
ma'am. Can you explain temporal coherence?
I will explain in here. So you have S1 source and there is a point P where you wanted to see if there is going to form any kind of, you know, fringes. So there is a wave which is coming from here. Similarly, there is a wave S2 which is coming here. So if there is a perfect relationship between them, you are going to see fringes. So what temporal coherence says is you have a wave S2 which is not perfect, have perfect phase relationship, meaning there is some glitch. You have a phase relationship and then there is glitch and there is some another form of phase. So that means up to here there is a phase relationship and this will represent there is a temporal coherence up to this region. After that the coherence will kind of changes and you will not going to see any pattern here. So necessary condition for the interference pattern to see is you have to have temporal coherence such that the wave which is coming from S1 to S2, they will maintain this phase relationship. So basically what temporal coherence says is how much your phase is going to relative for the two waves and it depends upon bandwidth of the source. Up to the bandwidth region, you will see the phase relationship maintained and beyond that bandwidth region, the phase relationship will get changed. So, are you able to get it
Yes, ma'am.
or should I explain it again?
Yeah, explain.
Okay, I will explain it simpler form. So you will see only, so you have a wave like this, another wave like this. So you will see a interference, you know that. So what if your wave gets changed somewhere here? Let's say you just switch off your laser and then again switch on. So in this case, till here, you have a relationship, but then it can change again. How could I say it? You are familiar with this concept of, I don't know, group and phase velocity.
Yes, ma'am.
So group velocity is generally used when you have bunch of waves, and when you have a just single wave, you are talk about the phase velocity there. So in case of, let's say, naturally all the waves are coming in the form of waves. They are not coming in just single wave form. So you have a kind of this envelope like thing, and inside this envelope you have these single waves. Mm, this is kind of thing. So this will represent how your whole group of wave are changing, and within this group the phase will remain maintained, and this will tell you bandwidth kind of thing. How could I explain bandwidth part? You are familiar with this Vib gear, right? It is used in white light, invisible range. So it is started from violet, it is will end on red. So whenever you talk about white light, you have a wavelength which is ranging from red to violet. So that means your wavelength will change from lambda r to lambda v. So your frequency corresponding to lambda r will be something. I'll show you. So corresponding to lambda r, your frequency is C nu r, which is C upon lambda r. So this is your frequency corresponding to red wavelength. Similarly, corresponding to violet, you have frequency lambda r by nu. And the difference between two, frequency for violet minus frequency for red. And this will give you some value since lambda is different these two cases. So C upon lambda mu minus 1 upon lambda r. So this difference between frequency. So you have full range of frequency which started from violet color to red color, and the difference between these two is known as the bandwidth of visible spectrum. Similarly, if you do not have a visible spectrum, it is some, like say, laser or some LED. They have a very small bandwidth, something like, in this case, the bandwidth is very high, but in this case, the bandwidth is like 30 nanometer, or in laser case, even it's smaller 10. For LEDs, where it's from 30 to 40 nanometer. So bandwidth is telling you how much spread is there in wavelength. So if your wavelength is, you already know that wavelength is given by this parameter, one cycle of the wave. So if this is your wave, then within, for the case of visible wavelength, this is your delta nu. So you have a very large bandwidth. That means you have very small coherence. In case of visible light, because coherence length is inversely proportional to bandwidth. Larger the bandwidth you have, smaller the coherence length you have. So here I have shown you in wavelength picture. This coherence, temporal coherence is in bandwidth. How could I explain it simpler? I don't know. So basically, it just tell you how much time your wave will maintain a particular phase relationship with itself, with another wave also. If your phase relationship will changes very early, that means your temporal coherence is very small. You have seen the sunlight. In case of sunlight, temporal coherence is very small. That means the wave 1 is not correlated with wave 2. That's why you see always uniform light across whenever there is a sun. But if you try to see the experiment using laser, which have very large temporal coherence, then you will see the intensity variation. Somewhere you will see dark, somewhere bright. And this is due to temporal coherence variation. Are you able to get it? Or I'm not able to explain it properly, maybe.
Yes, ma'am. Get it.
Okay, the space temporal coherence is related to the source property. It's related to wavelength, and the spatial coherence is related to the size of source, how much or big your source is, or how small your source is. So temporal coherence is related to your wavelength, but spatial coherence is related to the size of the source. So this we will start do it again, but I'm not going to tell you the temporal coherence thing again. It's too confusing here. Okay, the spatial coherence is related to the source size. So if you take a very narrow slit, that means you are going to create a very large wavefront, and whenever there is a phase relationship exists between the wavefront, then you can say that your points which is coming inside this region have a spatial coherence. You will learn this concept of spatial and temporal coherence again later. I will tell you the spatial coherence, maybe then you will understand what I mean by temporal coherence. So if you already know that why we use this source here in double slit experiment, can you place this S1, S2 as much large distance as you want and still see the interference pattern? Or there is some condition on an S1 and S2 to see the interference pattern? Means can you take D to be infinity, or there is some condition on D, how much distance should be so that you can see interference pattern here. So this is related to spatial coherence. It says that if S1 and S2 are outside the coherence region, then you will not going to see interference. For example, if your spatial coherence is lie within this region only, and S1 and S2 lie outside this region, then there will not be any interference pattern here. So for interference pattern to be seen in young double slit experiment, X1 and S2 has to be in coherence region. So how do you find that coherence region here? This will depend on the source size here. So basically, if you have a source here and S1 and S2 are just equal distance, such that this distance and this distance are equal, that means the wave that is coming from source are in phase for both the case, S1 and S2. There is a wave coming here, there is a wave coming here. They are in phase. So you are always going to see interference pattern in this case. But let's say your source is shifted to S distance. The condition now has changed. Your source is shifted to S dash. So the distance from S dash to S1 and distance from S dash to S2, they are different. That means there is a phase that is coming between S1 and S2. If this phase, this will kind of phase at time t equals to 0, so it kind of remain constant. So this will again give interference pattern, but it is not the same as this case. For this case, if you look at the O position, you are going to see maximum intensity since both have the same part difference here, and then you see this intensity variation. But here at the position O, there would not be maximum, it would be something else. And if it is such that the S1 and S2 has a phase difference of lambda by 2, that is wave coming from S1 differed by the path difference of lambda by 2 with respect to the wave coming from S2. Then at the position O, you are going to see minima. You are getting this concept? Just changing the phase that is coming from S1 and S2, you can uh, kind of translate your fringe pattern, something like this. At the position, if this represent O position in first case, then the second case is represent O position. So at the O position, it is maximum in first case, then minimum in second case. So if you have an extended source, I think you get this condition thing, these two. Are you able to get this condition? Otherwise, I will leave it then.
Yes, ma'am.
Okay, so if your source is S, then you will see maximum intensity at the center. But if it is S dash and S dash position is such that the path difference between S1 and S2 is lambda by 2, then you will see minima at O. So at this screen, if you have a source which size is such that it starts from S and it will end on S dash, then half of the part of this source will give you bright here and something like interference, and the remaining half part of this source will give you minima here and maxima here. So at the screen, you just see uniform intensity pattern. For example, if you take the average of these two, what you see? This is maxima, this is minima 0, this is maxima 1, so you see 1, just add. I'm just trying to add them. This is 1 and this is 0, 1, 1, 1. That means on the screen you just see a uniform pattern. So if your source size is such that S dash, which is the one extreme of source, and S, which is another extreme of source, they are kind of making a path difference of lambda by 2. In that case, there will not be an interference pattern. And mathematically, if we try to solve what that minimum width would be such that interference pattern will manage. We can say what is the source bit would be to see the interference pattern in double slit experiment. So this is what we are trying to do. We calculate the distance again the same simple one case. It is something like we have done in young double slit initially. We take the two slits and we place our source here S dash S1 S2 and we will calculate what is the path difference between S dash S1 and S dash S2. If this path difference is lambda by 2, then the intensity will going to be vanished on the screen. So here if we put S dash S2 as lambda by 2, we will see that the intensity will going to be vanished. Here A is the distance, this distance is the A, this is D, and the width here is W. So again we are going to do the same thing to calculate S dash S2 and similarly S dash S1 and we subtract them, then we will get the width. Now if this width is such that, then we are always going to see the fringe pattern vanish. So our source has to be much smaller than this width W. So this is the source width. Your source has to be smaller than lambda A by D to see the interference pattern in young double slit experiment. So this is the question that is asked in GATE 22 exam. A student set up young double slit experiment with electron. So just don't bother with electron here. All we have to change is lambda equals to h upon p for the electron. And they are giving the momentum p incident normally on slit of width w at a distance d. In order to see the interference pattern on a screen which is at a distance d from the slit, which following conditions should be satisfied? The condition that should be satisfied is that width of the source has to be less than lambda by d. Here A is the separation between this source and this slits. So here it is given as capital D. That means W, which is the slit width here, should be less than lambda capital D by D, and for electron lambda is h upon p. That means W should be less than h upon p into lambda capital D by D. That means HP is greater than WD by D. So this is H cross is given here. So this is the option that is correct for this question. So basically, you have to have the condition for the source grid to see the interference pattern in the present experiment. Okay. So next question. This is coming in GATE 2016 exam. So in young double
Ma'am,
slit experiment using light.
ma'am, hello. Please
Yes.
repeat again previous question.
Which one? First one.
This, yes, yes.
So the to solve first this question, you have to know that for a young double slit experiment, you have to satisfy this condition of coherence from the source, which is given by of width W. So the W should be less than lambda A by D for the coherence to be available onto the slit S1 and S2. S1 and S2 will be in coherence or have a definite phase relationship only when W is less than lambda A by D. So lambda is given by H upon P for the case of electron. This is de Broglie wavelength formula. So when you put the value of lambda as h upon p and a is replaced by capital D, which is the distance of the screen from the slit, W is less than lambda d by small d, and I just put the value of lambda here, then W will become less than h upon p into capital D by small d. And I just put take this value small d and capital D here. So this will give you option h upon p small d capital D by d. I think. Are you able to get it?
Yes, ma'am.
Okay. So this is the question from K 2016. In, win- in this question, it is given that apparatus has two slits of unequal width. Widths are not equal. And when only slit one is open, that means the intensity is coming from only one slit and it is known as I1. The maximum observed intensity is 4I naught. So I1 is 4I naught. When only slit 2 is open, that means only slit 2 is open. That means the intensity is I2. The maximum intensity is I naught. When both the slits are open, an interference pattern is seen on a screen. What is the ratio of maximum intensity to the minimum intensity? So maximum is, I think you are familiar with this concept. Intensity in case of interference is square root of I1 plus I2 twice of I1 I2 cos delta. And for the maximum case, cos delta is 1. So I max is given by this expression. And for minimum case, cos delta is minus 1. So here minus will came and then this is the expression for minima. And I just put the value of I1 here and the value of I2 in this expression. And this will become 3 times of square root of I naught square divided by square root of I naught square. So the ratio will become 9. Okay. So the next question is a monochromatic plane wave of wavelength 600 nanometer and it is given by this expression is incident normally on a grating, giving rise to a plane wave in first order of diffraction. And it is given propagating in the direction of K1. So what is the period of diffraction grating? So basically first you have to understand what is diffraction grating. Similar to like double slit, if you extend these slits up to n numbers, then it will become grating. So diffraction grating is the n slits. And the condition for the maxima of for the case of grating is given by t sine theta equals to n lambda. And it's a complete long expression to calculate this condition. I just use it directly here. So the concept here is we have to find what is the period of
Hello.
diffraction grating.
Hello. Hello.
Yes,
Well, uh, this is there is an and slit in
yes,
this question. We for the in the derivation we are only took two slits.
yes.
Yes.
It is not
So
going to valid for n slit. You have to see expression for n slit. Maybe
and
I will.
what is the condition for maximum in diffraction grating if there is a two slit?
If there is two slit, then it will become young double slit experiment. And the condition for okay. So you are asking this condition,
Yes. Yes.
then it will become the cos theta is a function of cosine. I will see where I have dragged the expression. So you have see the intensity I in case of I will tell you here. See, this is the expression for the intensity I when you have two waves. So the conditions it depend on this cosine of function. Cosine of theta equals to whenever you have d cos theta equals to n lambda. This is the condition for maxima. M lambda m plus 1 by 2 lambda. I don't remember it correctly, like m plus 1 by 2 or m, but it is a function of cosine of this term. But from here, I can see that for the case of m lambda, it is the maximum, and for the case of m plus 1 by 2, it is the minimum. But it is a function something like d sine of d cos theta. There is complete whole expression that will evolve from where this expression came. I do not remember it correctly. I will let you know. I will let you know in notes, or maybe I will give you NPTEL lecture link to let understand how this expression derive.
Okay.
Sorry, I don't remember it correctly here.
Never mind.
So you have a wave which is incident normally onto this diffraction grating, and in first order it will goes like in this direction. So we have to calculate what is the period of this diffraction grating D in this case. So um, you have an incident wave, let's say it's in Z direction. So let's say this is the Z direction, and you have a wave which is moving in this direction K1, which have both component X and Z. So this is X and Z, and this is your K1, and it makes an angle theta, let's say. So in this case, you can say that your incident wave is K with magnitude K in the Z cap, and you have K1 with magnitude K1 along with the direction which have both component X cap and Z cap. 1 by 2 X cap plus square root of 3 by 2 Z cap. So you have to know what is the angle theta. So this is the condition for diffraction grating, and we have to calculate D. So sin theta can be calculated as K cross K1. This is just right hand rule. Once you know two vector K and K1, you can calculate sine of theta by taking their cross product. So I just take the cross product and divide by their magnitude. So magnitude of K1 and K will cancel out, and K is in the direction of Z cap. So 1 by K1 is in the direction of 1 by 2. So this term will multiply cross term with this term will give you 1 by 2 in the Y cap plus Z cap plus uh, Z cap. This term will give you 0. So sine theta will become sine inverse of half. This is 30 degree. And when you put this into the expression, this one equals to lambda by sine theta, it will become 600 by sine 30 degree. So it is become 200 nanometers. So the gating period is 1.2 micrometer. They have asked the question in micrometer. This question is the same in an interference pattern formed by two current source. The maximum and minimum intensity are 9 A naught and I naught respectively. The intensity of individual waves are. So we have to calculate I1 and I2. We have given maximum and minimum, I max and I min. So we just put it equals to I max, and then we just take square root on both sides. Similarly, we put equals to I min and take the square root both sides. We just add and subtract these two equations. We will get I1 and I2 as 4 I naught and I min. This the formula based question. Now this question from GATE 2030. Interference fringes are seen at a plane z equals to 0 by the superposition of two plane waves. E1 is given, E2 is given, and we have to see what is the condition for the interference maximum. So we have to calculate what is the phase difference between these two waves, and just put difference equals to multiple of 2m pi. So phase difference for the this wave and this wave. This has the phase phi1, let's say k1 dot I minus omega t, and phi2 k2 dot r. We just subtract it and put equals to 2m pi. So this is the correct option for that. So generally, the question asked in GATE exam much easier. In 22, maybe the question is much harder compared to other years. This one, it requires a little knowledge of concept. Otherwise, it is also a formula base. I will add NPTEL lecture link for the case you wanted to know. what is the condition for maximum intensity and minimum intensity. And then I will post this lecture note onto this YouTube channel. You can download from there. So let me know if you wanted to understand something.
मैम
Yes.
आप ईएमटी पढ़ाओगे ना?
हाँ, जनरली EMTs के लेक्चर हैं.
तो मैम जैसे ईएमटी में जो ईएम वेव के आगे जो भी सारे टॉपिक्स है ना, जैसे
हाँ,
ईएम वेव इन वैक्यूम, ईएम
EM wave in conductors.
उसके
Generally, the question asked in EM wave in conductor.
यस यस, तो और
Hmm.
उसके बाद नॉर्मल नॉर्मल एंड ऑब्लिक्यू मोशन द रेडिएशन
Okay,
फ्रॉम चार्ज, these type of
okay.
topics we cannot cover. So
So you want
you,
me to solve this question? Means not question,
we
mostly derivation.
not question. We want to some study material
Okay.
from EM wave to radiation from stars. Yes, ma'am.
uh, I will provide
अगर
you
हम टॉपिक्स,
lecture. मतलब मैं
बट
lectures के
मैम
जो
यू आर टॉकिंग,
derivation है ना,
या
मतलब ये जो तुमने बोला अभी, एक तो oblique इंसिडेंट का और इनसाइड कंडक्टर का.
यस यस,
तो मेरे पास इसके
हाँ
नोट्स
हाँ,
हैं. मैं ऐसे आपको स्कैन करके इस पे डाल सकता हूँ, यूट्यूब वाले. तो यू कैन डाउनलोड फ्रॉम हियर. और
यस मैम।
एक
मैम
कंसेप्ट
जैसे
लिख
EMT,
जाते हैं. यस.
सॉरी मैम, क्या
यू आर
बोल रहे थे
आस्किंग
आप?
समथिंग.
यस मैम, मैं ऐसे कह रहा था जैसे EMT में जैसे ये EM वेव हो गई, उसके बाद पोलराइजेशन वगैरह, और जो आपने ये यंग
हाँ.
ये इंटरफेस वाला टॉपिक कराया था ना, ये कौन से टॉपिक्स का सब टॉपिक है गेट सिलेबस से? कि वी आर नॉट फैमिलियर
कौन
दिस
से
थिंग,
कौन से
इंटरफेरेंस,
वाला?
इंटरफेरेंस टॉपिक
ये
जो
EM
आपने
वेव के
कराया है,
बाद ही आता है. एक्चुअली
कौन से टॉपिक
EM
का
वेव का
सब
ही
टॉपिक?
पार्ट है.
अच्छा अच्छा अच्छा,
EM वेव का सब
तो
टॉपिक है ये. और पोलराइजेशन भी EM वेव का ही पार्ट होता है. पोलराइजेशन का वीडियो बना चुके हैं हम.
मैम आई एम नॉट एबल टू रीड EM वेव, प्लीज प्रोवाइड।
Okay, so uh, YouTube link is available on this
बस
NPTEL GATE lecture
या
course.
मैम, बट इन यूट्यूब वी आर नॉट एबल क्लियरली to watch,
Okay,
yeah,
so
because
I will
you are
provide NPTEL link.
there are lecture, but I want to some like get type of notes you have already.
Okay,
Yes
I will try to form the PDF file of all complete electromagnetic theory,
yes
the
yes
notes
ma'am,
that I have for my GATE preparation.
yes ma'am, that will really helpful for all of
So,
student.
okay, so what I will do, I will just try to form a PDF for you, and in which there are notes, there are derivation, and previous year GATE questions. The way trick, sometimes tricks are also used to solve some question which is given inside notes.
Yes ma'am.
So I will provide you in the next class.
Yeah, we will wait, but some doubt how we will send.
You will get the link on YouTube channel. I always
You,
provide some PDF link for the YouTube channel in description box of YouTube channel, so
yes
you
yes
can see in next class.
yes, We will get
Okay.
notes from next in next class.
Yeah, in next class. This class I have to upload like that.
Okay, ma'am.
Okay.
Today's class is very very helpful, ma'am.
So I will provide you notes for other things so you can see yourself what is necessary to read in EM wave, or you can see what is necessary to read in electromagnetic theory.
Yes, ma'am.
Complete.
Yes, yes.
Okay. You will get in next class.
Okay, ma'am. Thank you.
Okay, thank you.